In this video, I want to go over some of the related rates problems that we didn't get to in the notes just to explain it. And actually, just one, example 5, if you've got the notes and you want to follow along. I'm going to do both part A and part B. And then I'll show you a different example from online that I also want to talk about just to re-emphasize the process of finding or solving a related rates problem. As a reminder, you'll find this in the filled notes. But I showed you guys kind of a 5-step process in class. There's a 7-step process that's printed in the notes, but I think the 5-step process is sufficient to kind of being able to use this to solve any related rates problem. It's kind of our problem-solving process. So step 1, write down everything you're given in the problem, draw a picture. Step 2, write an equation that describes what's happening, the relationship between any of the given variables. Step 3, check to see if you need to make any substitutions. Step 4, take the derivative, use implicit differentiation, and it should always be with respect to time. And step 5, plug in and solve. And so you can find this in our filled notes on Google Classroom. But I'm going to do example number 5, also from the notes. And this is filled in really pretty on the notes. Sorry, I keep hitting the table. But if you would like to hear how we kind of use the 5-step process to get through it, I'll explain that here. So let me read the problem out loud. All right, so a ladder is 10 foot long, resting against a vertical wall. So the first thing I'm going to do is just going to draw my picture. I've got my vertical wall, and I've got my ladder. Maybe I'll make it an actual ladder. Okay, and that ladder is 10 feet long. Okay, if the bottom of the ladder is sliding away from the wall, okay, so sliding away from the wall at a rate of 1 feet per second. Okay, so I'm going to identify this as x. And this is all in step 1 of my 5-step process. I'm drawing a picture, I'm writing down everything the problem is giving me. So if I call this x and it's sliding away, then x is getting bigger. So the rate at which x is changing with respect to time, dx dt, is equal to positive 1 feet per second. Okay, so the bottom of the ladder is sliding away from the wall at a rate of 1 feet per second. How fast is the top of the ladder sliding down the wall? So how fast is this going this way when the bottom of the ladder is 6 feet from the wall? So let's call it, this is x, I'm going to call this y. So we want to know how fast is y changing with respect to time when the bottom of the ladder, x, is 6 feet from the wall. So this is kind of our goal. This is what we're going to solve for. Okay, and that's all the information in the problem. So I can move on to step 2. I need to write an equation that relates x, y. Well, I guess I could use some trig here, but I've got 3 sides of the triangle, so I'm going to go with my Pythagorean theorem. I'm going to say that x squared plus y squared equals, and I'm going to call this z. And you're going to be like, well, Ms. Kelly, we know that it's 10 feet, but I just want to prove something to you really quick. Okay, so I've written an equation, step 2. Step 3. This is where I check. I count how many, 1, 2, 3, how many variables are in my equation? 1, 2, 3. How many derivatives do I have? 1, 2. And that's where I know I'm in trouble. I need to make a substitution. If this number of variables doesn't match the number of derivatives am I given, I need to make a substitution. The good thing we know is that since the ladder length is 10 feet, the length of this ladder is never changing. So the rate at which the length of the ladder changes with respect to time is 0. Okay? I'm going to write that. The ladder isn't changing lengths. So you can think of this 2 ways. You can either, knowing this, now think I have 1, 2, 3 derivatives and 1, 2, 3 variables, and you're good to go. Or you can sub in z equals 10 here, because you know that z will always be 10 no matter what x and y are. Okay, so I'm just going to do it. I'm going to go ahead to step 4. Okay, and I'm just going to use this as like another given that I discovered. So if I take the derivative implicitly, I will get 2x dx dt plus 2y dy dt. Remember, you're always using the chain rule. Equals 2z dz dt. And this is where you can see like, oh, well, I'm going to sub this in and it'll get 0. And you'll get the same result if you had plugged in 10 here, because the derivative of a constant would also be 0. So it's just going to be equal to 0 anyway. All right, we've done step 4. Great. Great. Step 5, we just substitute in everything that we were given. Okay, so 2, and in our given x was equal to 6, so 6, dx dt was 1, plus 2 to, I don't know what y is, and I need it. Luckily though, I can use this when in the instant that x is 6 to figure out what y is. Well, if we think about this as really a 3, 4, 5 triangle that's been multiplied by 2, 6, 8, 10. So y is going to be equal to 8. And you can also use the Pythagorean theorem and actually solve that out to prove it to yourself. I am looking for dy dt. Okay, 2 times 10 times 0. All right, and that's my setup. Now I'm just going to solve for dy dt. So I've got 12 plus 16 dy dt equals 0. So dy dt, and let me make sure I'm really clear on my notation. When x equals 6 feet is equal to negative 12 over 16, which if I would like to reduce, remember you don't have to, I could divide everything by 4, and I would get negative 3/4 units feet per second. Now you always want to check yourself. I'm sorry, I scoot over. This is a negative number. The rate at which y is changing is negative. That means that y is decreasing in size. Does that make sense? Oh, yes. My ladder was falling down. This should be getting shorter. So this should be a negative number. And we're done. In part B though, same setup, okay? The question is, how fast is the angle between the bottom of the ladder and the floor changing when the foot of the ladder is 8? So new question, what is d theta dt, the rate of change of the angle, when x equals 8 feet instead? Well, we can't use the same setup because this didn't involve any theta anywhere. So I have to rethink about step 2. So this is, again, step 1. This now, with all of this also happening. Step 2, and this is where you have some choices. Now, I think the smartest choice, or the, just in case you messed up somewhere in here, the smartest choice is to use what you were given to write the equation. So as if we had never even solved for y. We had never solved for dy dt, nothing like that. Use what the problem originally gave you. Well, they gave you dx dt, and they gave you the length of z. So I need a relationship that relates this angle, x, and z. Okay, and that should be cosine. So I have adjacent. Cosine of theta would be adjacent, which is x, over hypotenuse, which is z. Okay, step 3, again, I want to check. I have 1, 2, 3 variables, and this is one of those ones where, yes, dz dt is going to be equal to 0, but I don't really want to do the quotient rule, so it might make more sense to substitute 10 for z here, because that's a constant. Because then I can think about this as 1/10 x, which is a lot easier to take the derivative of. Let me scoot this up. Okay, so I'm going to think about it that way. So step 4, take the derivative implicitly. Well, the derivative of cosine is negative sine theta, chain rule, d theta dt equals 1/10 dx dt. Okay, now I can substitute. I will get step 5. Okay, well, shoot, sine theta. How do I even figure that out? Well, let me draw a little triangle over here again. At the instant, remember when x is 8, I will have 8, 10, and again, I have a 3, 4, 5 triangle, so y will be 6. So sine of theta will be, this is theta, opposite over hypotenuse. So I can just subset in right here instead of having to solve for this angle, which I still don't know. And yes, you could solve for the angle a different way, and that's totally fine. This is just one possible way to make it a little bit easier. So I'm going to say negative 6/10 d theta dt. Sorry, I keep hitting this camera. Equals 1/10, and then dx dt we knew from the very beginning. Still up here, it's 1. Okay, so if I solve for d theta dt when x equals 8 feet, I should get 1/10 times -10/6. So -1/6. And we are going to be in radians. This class is always in radians. Radians per second. Okay, that's my final answer. And does that also make sense? Well, remember that the ladder is sliding down the wall, so the angle is getting closer to 0 as it kind of flattens out. So that does make sense in the context of our problem. Okay, so that was example 5 from the notes. And I just want to do one more problem that I found online. Again, remember, you can just look stuff up and practice. There are a lot of great keys online. All right, so this might be a little wide for the screen, but I will read it to you. So sand is being dropped onto a conical pile. Okay, so if I'm dropping sand, that means I'm going to make a cone this way instead of an inverted cone. Okay, so I've got sand kind of like dropping, making a cone. All right, at a rate of 10 cubic meters per minute. So we've got a volume of sand. Cubic meters always tips me off that it's volume. So the volume of the cone is changing at a rate of, and its sand is being added to the pile, so it's positive 10 meters cubed per minute. Okay, if the height of the pile, so the height of the pile is always twice the base radius. Oh, they are giving us a ratio, twice the radius. So this is height, this is radius. Okay, at what rate is the height increasing? So they want to know dh dt, the rate of the height is increasing, when the pile is 8 meters high, when h equals 8 meters. All right, so step 1, complete. Drew a picture, wrote down all the givens, including this ratio that will come in handy. We're on to step 2. And if you don't remember, we have that the volume of a cone is 1/3 pi r squared h. Okay, all right, so we're ready to go there. We've written our equation. Step 3 is where we need to check. I have 1, 2, 3 variables, but only 2 derivatives. That's where this substitution will come in handy. I want everything to be in terms of h, so I want to substitute r. So I have 1/2 h equals the radius. That's what I'm going to sub in because I want to get rid of all my r's. I want to solve for something in terms of h. So I will substitute volume equals 1/3 pi 1/2 h squared times h. Before I take the derivative though, I definitely want to simplify that. So I have volume equals 1/3 pi times 1/4 h squared times h, which is 1/12 pi h cubed. We're ready to go. Now I have 2 variables, 2 derivatives. Solid. Okay, so 4, take the derivative implicitly. The derivative of volume with respect to time will be 1/12 pi 3h squared dh dt, chain rule. Okay, and then I can plug everything in step 5. So I've got dv dt, which is 10, and then maybe I can simplify this a little bit. So I get 1/4 pi, and then h is 8, so I will get 8 squared dh dt. Okay, all I have to do is isolate dh dt now. So I've got dh dt when the height is 8 meters is 10 times 4 divided by pi times 8 times 8. And I like to write it out like that, and you don't have to do this again, but just in case this is a multiple choice problem, I can simplify really easily. So here, I'll be left with a 2. I can eliminate that as well, because I'll be left with 5 here. So I will get 5/8 pi, and my units, this is height, so it should be linear terms, so meters per minute. That's my final answer. Okay, so, and I wanted to show this problem again because we want to make sure that you're checking in step 3 to make sure you do a substitution.